Hello there, this is another video for chapter 5. I hope you're doing well. So let us get started. I'm going to work on this section, 5.3, which is the fundamental theorem of calculus. It has two parts. So we're going to do the part 1 first, obviously, and then part 2. And in order to prove it, we need a theorem. It's called the mean value theorem for integrals. Now, we know that, get my pen here quickly. We know the mean value theorem for differentiation. The mean value theorem for differentiation is when, let me give you an example. So if you have a function, and the function, let's say we go from a to b, the mean value theorem for differentiation says that the rate of change, if this is f of x, then the rate of change from a to b, which is f of b minus f of a over b minus a, that rate, which is basically, if you connect from here to here, is the slope of that line, which is a secant line, right? So the mean value theorem for differentiation says there has to be a number, at least a number between a and b, where at that number the instantaneous rate of change, which is the slope of the tangent line, is the same as the slope of the secant line. And that point in this case looks like it is over here, right? So there is a c here where, what is the instantaneous rate at c? That's f prime at c. So f prime at c equals to that, which is the slope of the secant line. So that is the mean value theorem for differentiation. Now the mean value theorem for integrals says that if we have the same situation, let's say we have a function, and then we go from a to b, and the function is continuous, the area under this, the area under f of x. Now what is the area under f of x? Well, the area under f of x is given by, if this is f of x, the area under it is the definite integral from a to b, f of x dx, right? So that's the area. So this theorem for integrals says that there has to be a number here between a and b such that when let's say this number here, when I find the f at that number, f of that number is going to be the area divided by b minus a. And this number is actually the average value of the function. So the average value of the function, you see, function has many function values here, right, at different x values. So the one that is the average of all of them is given by some number here, right, f of some number between a and b, and that number is going to be such that f at that number would equal to this, f. So f at c equals to f average, which is this. Okay, so that's the mean value theorem for integrals. And we talked about f average already, so we know what f average is. This is f average. So this theorem says there has to be a number such that f at that number equals to this f average. Okay, so let me give you the statement of the theorem, and then we need to use it to prove the other theorem. So notice that that's exactly the same thing, right? So f of c equals to that. So as we discussed with f average, that means that if you have a function f of x, right, the area under it between a and b divided by the distance between a and b is f at c, and c is a number between a and b. And this of course is what is the f average. So this theorem says there has to be a number between a and b such that f at that number is f average between a and b. Okay? Now if you multiply both sides by b minus a, this is what you're getting. That the area under a curve equals to what? F at c times b minus a. Okay? And that idea is that if you have a function, let's say we have a function here from a to b. Let's say that's the function from a to b. So the area under this is the same as if you find that c, let's say that c is over here, then if you make a rectangle from A to B, the area of that rectangle is the same as the area under the curve. That's what this is. See, the area under the curve is the same as f at c, which is the height of this rectangle that I drew here, right? This rectangle here. So the area of that rectangle is the same as the area of the rectangle, right? B minus A is the length and the height is the same as area under the curve. That's the idea. Now we're going to have to use this in order to prove the fundamental theorem of calculus. All right, so let's first look at an example. So here's an example. It says find the average value of f between a and b and find a point c where f average equals to f of c. Now, we're not going to be able to do this with formulas that we're going to learn in this section, because in this section we're going to learn formulas to quickly find this. But what we are doing here is to prove those formulas. So it's going to be a kind of a circular reasoning if we use the result of a formula to prove it. That doesn't make sense, right? So we're not going to be able to use the formulas to find this area. We have to use the old limit method that we discussed before in other videos. But in this section, I'm just going to give you what this equals to, so we don't have to do the limit and all that, right? So we assume that the area under x squared from -1 to 1 is given by 2/3. We're going to use this value. So we know the formula. So this is a function, right? And that's what it looks like. So let me give you, this is x squared from -1 to 1. That's the area, the brown area here under the curve. The brown area, which is basically all of this, right? All of that and all of this, right? That is what this is, right? And we know that is 2/3. Now, there has to be a number. There has to be a number between -1 and 1 such that at least one number, there could be more, but there is at least one number such that f at that number, let's call it c, is equal to f average, which means f at that number is equal to the area under the curve divided by b minus a, right? Now, what is the area under the curve? Well, is this right here, and we just talked about the fact that is equal to 2/3, right? So that's 2/3, and then b is 1, 1 minus -1 is 2, so that's 2 in the denominator. So we need to find a c such that f of c equals to this number, which is 1/3, right? Now, what is f of c? F of c is f of x when we substitute c for x, right? So that's c squared. That's f of c. What is it supposed to equal to? It's supposed to equal to this number, 1/3. So we have to find a c that makes this true, and looks like we have two numbers that make that true, right? So we got two c values, 1 over square root of 3 and -1 over square root of 3. You just have to take square root of both sides, right? Now, when we substitute 1 over square root of 3 for x, let me clean this mess. So if we put, if f of x equals to that, if I put 1 over square root of 3 in there, square it, I just get 1/3, right? Even negative 1 gives me the same thing, 1/3. So f of plus and minus 1 over square root of 3 is just 1/3. So, so that's 1/3, right? And so we got two numbers. The square root of 3 is about 1.7 something. So 1 over the square root of 3 is about point something, which is right here. So this is actually the square root of 3, positive 1 over the square root of 3, and this is negative 1 over the square root of 3 approximately. Okay, now notice that if I make the height at this point, I get this number, and if I make a rectangle from negative 1 to 1 using that height, see the blue area here? The blue area is basically f of c. We got two c's, but it's f of c. The height is f of c, and the length is negative 1 to 1, which is 2, right? And 2 times f of c, right? And we know f of c is 1/3, so 2 times 1/3 is 2/3. That's exactly the area under the curve. So here you see that the brown area, which is this whole thing, all of that, that's the brown area, is equal to the blue area, right? So that's the idea of mean value theorem for integrals. All right, now this is the fundamental theorem of calculus part 1. What it says is that we're going to assume that we have a function, capital F of x, and that function we're going to call it the area function, right? That's the area function. What does that mean? It means that if you have a function, let's say f of x, and you fix the point here at a, there you go, that's f of a right there. So we're gonna, and this function goes maybe this way and that way forever. So now we're gonna pick a number, let's say x here, and then we're gonna find what? We're gonna find the area under this. Well, we know what that is. That would be a definite integral of f of x dx from what? From a to x. But if we put an x there, we can't use the same variable here, right? Because we use x to indicate the top index, the upper index right here for the integral. So we're going to use t for the function, and we're going to call this axis t-axis, but the value of this second number that we get here, we're going to call it x. So that's what the area is. Now, if we go to different x's, different x values, right? So let's go x1, x2, x3, and so forth. Then we get different areas for every one of them. Let's say this is x1, so we get a of x1. And then we can actually do it again and do x2. So what do we do? What do we get? We get, f of t dt from a to x2. So we don't change a, we keep a fixed, and then we move to the right or to the left. We could also go this way, right? Let's say we get x5 here, and then this area right here. That would be a negative area because we go to the left, but still, a of x will give you a value. So if you take all of these values, x values and a of x values, right? If you take all of these values and then find a pattern, that pattern is what this function is all about, and that function is called the antiderivative function actually. So let's look at an example here, and I'm going to do this with the program GeoGebra. Open, and I'm going to create a function. I'm going to call it f of x is easier to work with x here. So f of x equals to x to the third power. So that's my function, right? There you go. And what I'm going to do with GeoGebra, I'm going to create area under it by approximating it. And to do that, I use a command called rectangular. If you start typing RECT, you see it right there. So that's rectangular sum. And the function is f. And I'm going to go from A to B. How many rectangles? N rectangles. And then the last number tells the GeoGebra program whether I want left end point or right end point or somewhere in the middle. So that number, I'm going to call it P, position. And then I'm going to be asked whether I want to create those, and I say yes. And what I'm going to do now, I'm going to fix A. So I have to give him some values. So I right click on him, and over here you can actually set up the values for A. So that's good. I'm going to go with the step of 0.1 for my A. So it goes from -5 to 5 and goes 0.1 step. Then I click on B and do the same thing here. So I'm going to go step by 0.1. Then I'm going to click on N. Now N, I just want it to be starting from 1. That's number of rectangles, 1 to 50. Okay, that's good enough. And I'm going to increment would be by 1. So I can change it like from 1, 2, 3, 4. And then P, that's something that the GeoGebra uses. So I make it be from 0 to 1 and go again by 0.1. So if you set P equal to 0, it uses the left end. If you put 1, it uses the right end. Okay, so that's good enough for me. So now what I'm going to do, I'm going to set, we want here in this problem, we want A to be 0, right? Because we want to start from 0. So I'm going to set A to be 0. There you go. And then I'm going to set B. B, of course, could be any number to the left and to the right of A. And number of rectangles, I'm going to, for now, make it maybe 10 rectangles. Okay? So what we want to do, I want to use 10 rectangles to estimate the areas from 0 to 1, from 0 to 2, from 0 to 3, from 0 to 4, and so forth, right? So what I'm going to do, I'm going to go make B 1 right there. So this number right here is the area under the curve when I go from 0 to 1. So this area is approximately 0.3. And then from 0 to 2, in order to find it, I could just go to what? Make B be 2, and it's going to go off the screen because the function values are big, right? But that's okay, we can bring it back right here, okay? So from 0 to 2 is going to be 4.84 and so forth, okay? All right, now what I'm going to do, I'm going to create a point, capital A equals to, you put parentheses, inside the parentheses, you're going to put the x and the y value of the point that I want to graph. Now, what I like the point to be, I want the point to be, the x coordinate to be b, which is the upper limit for my integration, right? You see, b would be the x value. So I want to graph points with the x value to be x, which in my program here is b, right? B is my upper number. So I put b, comma, and then the number, the value of the area is given by this number c in GeoGebra. So I just put c. And then press enter. And now you see that A right there? A is the number that as I move B, what A does, A shows the value of the area. Now, if I right click on A, either here or here, doesn't matter. If I right click on it and turn on the trace on it, and then do this, now notice it leaves a trace that where the area value was, and that trace is what? Is the antiderivative function. What is the antiderivative of t to the third power? Well, we know t to the third power, the antiderivative, I'm going to put it here. I'm going to put integral of my f, and the GeoGebra automatically graphs it. See, that red one is actually what is the antiderivative function. Then I almost got it, right? You see, it's not exactly the antiderivative. Why? Because my approximations are not really precise, they're not accurate. Now, how do I make it be more accurate? Well, I'm going to zoom in and out to clear the screen. Then in order to make the approximation better, I'm going to increase number of rectangles. Instead of 10, I'm going to make it maybe, 50 maximum. And now look at the dots. They're exactly hitting the target, almost, not exactly, but pretty close, right? See, you're actually creating what? The antiderivative function. So the antiderivative function is really nothing but the area under the curve when you fix what? When you fix this number right here. And then you change this number. For every value of x, you get a value for area function, and if you graph the area function, you can get a curve that is close to the antiderivative curve. Now, you can do this with the calculator. We've done that before. You can go to L1 and L2 under, let me just show you where these things are quickly. So if you go to Stat and go to Edit, under L1 and L2, you can put these numbers, and then you graph it under Stat Plot, and you can see these 5 points. And then to graph the antiderivative, you can go to y equals 2 and just put the antiderivative function there and graph it. So I use GeoGebra to demonstrate this, because GeoGebra does this much quicker. Not only calculates all of these, but graphs them at the same time, right? All right, so that's the idea of area function. Now, the fundamental theorem of calculus part 1 says that that the rate of change, and here is in the notes, you can click on this. Let me click on it, and you can do exactly what I just did. You can even download this program and play with it from the PowerPoint file. And here you can change the number of rectangles, you can change number of the upper limit of this definite integral, and see how this is moving, right? You see that? So now I use like 400 rectangles, and you see I'm hitting the antiderivative function for x squared, which is x to the third. Now remember, when we talked about antiderivative function, antiderivative was not just one single function, but was a family of functions. How do you get the rest of them? Well, that is depend on the initial value. So if you change that initial value, which is a here, let me clear this. So I change the initial value. Now the antiderivative that we get is a different one, you see? It moved up a little bit. See that red one? Moved up. If I change the initial value maybe over here, and then do it, I move b. Now you see it's way up there. You see, it looks the same, but it moved way up there, right? Let me do it again. See that? So if I move the initial value maybe over here somewhere, then it's gonna go somewhere else. You see that? It's the same shape. All right, so you can play with this, and but what does the fundamental theorem of calculus part 1 say actually? It says that if you take the area function and take derivative of it, the derivative of the area function would be this function evaluated at x. That's it. That's the idea. So basically it says that if you have let's say t squared dt from, let's say, 0 to x, right? If this is the area function. Now if somebody says, what's f prime of x? That means the rate of what? The rate of the change of area with respect to x. Well, that would be just t squared evaluated as x at x. So it would be x squared. That's it. Right? So it makes it easy to find the derivative of an integral. All right, now how do we prove this? Well, first of all, why do we need this theorem? Well, because we have, as I said before, in observations, what we get is actually derivative, right? That's what comes from observations. And in order to find a function that kind of is the pattern we're looking for, we have to integrate this derivative in order to get the antiderivative. Now, there are many situations in application problems where this is not possible. We can't get a formula out of here. So we can't get a formula for that f of x, but we know how to get the values of f of x using this process, and we can use approximations to do it. So it's important. This is a very important theorem. Okay, so let's prove it. There is a way that the textbooks proves it, and I'm going to prove it differently here, a little bit differently. So let's do that. So again, we have f of t here, right? And we are going from a to some number x1. Now this is x, of course, but different values of x would be over here, x1, x2, x3, and so forth, right? So we want to know what is a prime of x. And in order to figure out what the formula is, we're going to call x x1. So we say, okay, if what is a prime at x1, right? What does that mean? That means when I'm over here and I'm moving this number, right, area is going to get bigger. Before, the area is this much. After a little bit, maybe delta x change, the area would be this much. So what's the change in the area, and what is the rate of that area changing? That's what a prime is. So what is a prime at this point? Okay, well, first of all, we understand that delta A is a change in area, would be area up to x1 plus delta x, which is the whole area here, right? Which is all of that. And then minus area to x1, which is this part right here. Right? So this big area minus this area, that's delta A. And I have indicated what delta A is. Delta A is all of this. That's delta A, right? Including that part, this part right here. There's a little triangle and there is a rectangle. Okay, so that's delta A. Now, what is A prime? Well, we know the derivative of a function is given by what? Is limit of delta A over delta x. Delta A is like delta f, right? Delta y, right? Or f values, function values. So a prime at x1 would be limit of delta a over delta x when delta x goes to 0. And we know delta a, we already know what that is. Delta a is the difference between area at x1 and at x1 plus delta x. And then over delta x. We have to take the limit of this when delta x goes to 0 to find a prime at x1. Right? Okay, we're going to do that. So first of all, we are going to set it up this way. We say delta A is this trapezoidal kind of area right here, right? That's delta A. Delta A is between this area of this big triangle right about here, right? So it's that one right there. That's that. And then is obviously smaller than that and is bigger than this smaller rectangle, which is over here, which is that right there. Now we know the area of the smaller rectangle is what? Is the distance here, which is delta x, times the height, which is f of x1. So f of x1 times delta x. And the area of this big rectangle is delta x times f of x1 plus delta x, which is that big one right there. Okay, so now we're going to write that with algebraic formulas. This is delta A, this is f of x1 delta x, and this is f of x1 plus delta x times delta x, right? Remember, our goal is to get limit of delta A over delta x. That's what we are trying to achieve. I want a limit of this. We're going to build this. How? Using this the structure here. So what do we need? We need delta x in the denominator, so we're going to divide everything by delta x, and we can do that because delta x is a small positive number. Okay, we do that. Now these go away, right? In the middle, we get what we want. Now, we're going to take the limit as delta x goes to 0. Now, limit of this as delta x goes to 0 would be just itself, right? Limit of this when delta x goes to 0 would be f of x1, right? Limit of this is exactly what we're looking for, is the derivative we're looking for. So it looks like the derivative is in the middle of two limits, which is the squeeze theorem. So by squeeze theorem, the limit in the middle has to be the same as the limit on the left and the right. And that means that the limit in the middle, which is the derivative at x1, has to be f of x1, right? So the limit has to be f of x1 too, because those two limits are f of x1, right? This one and this one. All right, now we're going to say, okay, we found out what a prime is. So the rate of change of the area changing at this point, a prime at x1, is basically what that function is, f, inside the radicand, the integrand, right? Inside the integral symbol, integrand. So whatever that function is at x1. So if I move to another point, doesn't matter. This formula still works. So I just say that a prime of x equals to f of x, right? Obviously, we use a dummy variable t here because we want to use x on the top here. You can use some other variable, put y here and use x here, doesn't matter, but that's the convention. We use t here and x here. So a of x, the area function, is defined by this. Then the prime of it is basically f of x. All right? Now, if you click here in the notes, you can see the proof in the textbook. And I'm going to now go back and look at this again one more time. I'm going to look at what we have here online. This time you can see the rate of change of the area function here. So you see right there, it says dA dx, that's the rate of change of area changing. And then this is f at, this is f at the upper limit of the integral. So as I change this b here, obviously the area is changing. Let me change the number of rectangles for now to maybe a small number, maybe 10 is good enough, okay? So you see, compare this rate to this rate. Obviously they're not exactly the same, but as I move, they change, and notice that they're kind of the same, but not exactly the same, you see it? 0.55, 0.60, not exactly the same. Now, in order for them to be close to each other, to kind of confirm the theorem that we just talked about, we can increase number of rectangles to like maybe a large number, and then do it again. Now you see the rate is pretty close. By 1 decimal place, they're the same, right? And that is actually true. So you can confirm this. You can actually change a function here too if you like. We use a different function. Again, this relationship would not change. Let me use some other function. Let's see, maybe cosine x. Of course, this is I zoomed in and out too much, so maybe I should just use a polynomial, maybe x to the, I don't know, third power, or maybe x to the second power. There. So use a polynomial. The program is sensitive because of the scaling and all that. But again, this relationship doesn't change. You see that? The values are basically the same. This is the function value. This is f of this b value. And this is the rate of change of area at that point. And they're the same. Okay, so that's the idea of fundamental theorem of calculus part 1. And we just proved it. Now, the second part of fundamental theorem of calculus is called the evaluation theorem, and it's really the reason we can get things done in sciences, in many fields. The reason is because we have calculus and we have this evaluation theorem. So in application problems, when we are given some kind of observation here, right? Then using evaluation theorem, we can find the area, the accumulation under it, let's say from A to B, right? Now, this is accumulation of whatever is changing, right? If f of t represents the height of a graph, of course, the accumulation would be area. If f of t represents, let's say, a rate of profit, then this integral will give accumulation of profit, how much profit we have made from A to B. If f of t is how much oil is spilling, rate of oil spilling, then this integral gives how much oil is accumulated from A to B, if these are times, right? So it's a very important theorem. It allows us to evaluate this easily if we have the antiderivative. So this theorem says that if you want to evaluate this area under this function, all you have to do, find out what capital F is, which is the antiderivative of this function, and then just put f of b minus capital F of a. That's it. That's this theorem. And it's very, very useful. Okay? All right, so let's talk about it. And you can read this and you see how useful calculus has been in the history of sciences. So this is the theorem. The theorem says the part 2, right? Remember, fundamental theorem of calculus part 1 says that if you well, let's call this, I'll call it A, we can call it capital F of x. The part 1 says that if we have a area function defined by this, right? If you want to take the derivative of it, derivative would be just f of x. That's it. Just put the x here. That's the part 1. Part 2 says that if we have a definite integral, we can actually evaluate it how? Using the antiderivative of f of x, which is capital F of x. Right? So if I know antiderivative of f of x, I could just evaluate this easily by doing this. Now this makes sense because remember, the meaning of this is the area under what? Under a curve, right? So this says that basically let's keep this. Let's keep a, let me go over here just a moment. So I'm going to give a function. I'm going to start from 0, right? So I'm going to start from 0 and evaluate the area under this function, right? So if I start from 0, when I go to a, what do I get? Well, the area from 0 to a would be that much, right? So that means this area is nothing but integral from 0 to a of f of x dx, right? Now, when I go to b, well, then area over here, this whole area right there, all of that, would be integral of what? From 0 to b, f of x dx. But we know what this is. This is the accumulation area function at what? At a. And what is that? That's the accumulation from 0 to b, which is what? Which is f of b. So the area between a and b, so if I'm looking for area only between a and b, right? This area right here between a and b, I could take the area from 0 to b and subtract area from 0 to a from it. So it makes sense intuitively to have that formula. But how do we prove it? Well, to prove it, we have to start with this and somehow get this out of it, right? So that's how we want to prove it. Let's do that. So we're going to start by doing this. We want to prove it. We go to the interval from a to b, and we're going to divide it into partitions. How many? N of them. N partitions. So the first one would be x of 0, this number right there. And the last one would be x sub n. So b is x sub n, and a is what? X sub 0. And we have n, we have n partitions, so these numbers go from 0 to n, right? There are n distances between them, n units. But the partitions, the numbers that we need to mark the partitions is one more than how many partitions we have, right? So you see, if we have 2 partitions, how many numbers we need? We need 3. If we have 3 partitions, how many numbers we need? We need 4, right? So if we have n partitions, we need n plus 1 numbers. And those numbers are from x sub 0 to x sub n, right? All right, so that's the idea. Now, so we have partitioned this interval into n parts. This one is x sub n, and the first one is x sub 0. All right, now, f of b minus f of a is not what we want. We want to get, remember, we want to get this. Integral from a to b of f of x dx. How do we get that? Well, in order to get that, we know this is the limit of what? This is the limit of a sigma, right? So we need to get our sigma here, the structure of the sigma under control. Well, the structure of the sigma, we start with f of b minus f of a, right? Which is actually f of x sub n minus f of x sub 0, because that's what a and b are, right? And in order to make this look like a sigma, we have to have more terms. This is only 2 terms. So what do we need in algebra? If we need something, we add it and subtract it. So what do we do in order to get this? We subtract f of xn minus 1, and we add f of xn minus 1. We subtract f of xn minus 2 and add f of capital F of x sub n minus 2. Then we subtract f of x sub n minus 3 and add f of x sub n minus 3, and so forth, all the way to what? F of x1. So we subtract f of x1, and then we add f of x1, and then the last one, we keep it as minus f of x sub 0. Now, if you do that with this trick, you create a bunch of terms, right? If you group them like that, which gives you the sigma that we need. When I equals to 1, we get this. When I equals to 2, we get the next one. The order is reversed, but that's what you get, right? If you expand this, and then when x equals to n, you get this, right? So you get this sum of these terms, which is actually that sigma. All right, we're almost there. Remember what we wanted? We wanted to get the integral of f of x dx, right? And we want that to be f of b minus f of a, right? Now, in order for that to be equal to that, it has to be equal to a limit of a sigma when n goes to infinity, right? And that sigma is what we are building. Now, this is not good because we want to relate it to what? To the f inside here. So what do? We're going to use this idea. We're going to say, in our intervals, when we divide this into n intervals, partitions, right? Every partition, according to what? According to the mean value theorem for integrals that we talked about, and the mean value theorem for derivatives that we talked about. So according to mean value theorem for derivatives, this CI for every subpartition here, for every partition of this A to B, we have a C here, C1, C2, C3, such that f prime at C1, that means derivative of area function at C1, has to equal to what? The slope of the secant line from x sub I to x sub I minus 1. So in this case, this has to equal to f of x1 minus f of x sub 0 over x1 minus x sub 0. This C2 right here has to equal to f prime of C2 has to equal to what? F of x2 minus f of x1 over what? x2 minus x1, and so forth. Every one of these C's has to equal to what? A structure like that, according to what? Mean value theorem for derivatives. Okay, now from here, we could just cross multiply. We get that f of x sub I minus f of x sub I minus 1, which is this structure we're going to change, is equal to f prime of Ci times what? That. But by fundamental theorem calculus part 1, we already know that this is what? Is f of C1, right? So let me explain that part. So this right here, if you think of the integral, right, from A to B, let me erase this. So if you think of integral, let's say from xi minus 1 to xi of capital of f of x dx, right? If you want to find the, and if you keep the lower limit, constant, not change it, then this right here equals to, well, capital F of x, right? That's the area function from this number to this number, from x sub I minus 1 to x sub I, right? Just ignore that little segment I put there. So that is the area in that integral, area function in that partition, And according to what? According to the part 1, if I want to take derivative of this, right, then there has to be a number between x sub I minus 1 and x sub I such that, let's call this Ci, such that f prime of c equals to f of Ci, right? So this part right here can be replaced by that. Okay, now we have something. Now we can say that this structure equals to this summation, which is equal to this summation, which we recognize, right? Because Ci is here is like the x star sub I in this interval, in this partition, that in each partition that we talked about before. Remember, in order to do definite integral, we had Riemann sums. We have to take a number in each partition, right? And we called it x star sub 1, and then the next one would be x star sub 2, and so forth. You can think of Ci's as what? X stars. So basically, if you let n go to infinity now, here, take the limit of it, we get exactly what we wanted. So we just proved that that equals to what? To this, and that's evaluation theorem. That if you want to evaluate a definite integral from a to b, you can use the antiderivative. Right? All right. So make sure you go over this one more time to make sure you understood the proof. Now again, if you're in engineering, not pure mathematics major, you may be able to get away with not completely doing proofs, but there are a few proofs that I have done in this course, and this is another one of those, right? And some other ones that referred you to the textbook, okay? All right, so again, here is the theorem. Now we're going to use it. Here's an example. So how do we do this? Well, we're not going to set up a, partition the rectangle from the interval from 0 to 1 into n parts, right? And then take the limit of that and decide whether we do left or right, all of that. No. All we have to do to evaluate this is what? Find out the antiderivative of x squared, which in the next section we're going to learn easily. We did it in end of chapter 4, but we're going to learn more about that. But from end of chapter 4, we know the antiderivative of x squared is what? What's antiderivative of x squared dx? Is x to the third over 3, right? Remember? The formula for antiderivative of x to the n dx was x to n plus 1 over n plus 1 plus c. But we don't care about plus c in this section because that c gets cancelled when we set this up. So we have to find capital F of x, which we did, is x to the third over 3. Then we have to evaluate it at b and at a. So this is going to equal to capital F of 1 minus capital F of 0. That's it. And capital F of 1 is nothing but what? 1 to the third over 3 minus 0 to the third over 3. And that's it. And that's 1/3. So the exact value of this is 1/3. Right? And that is the answer. Okay? And you can stop the video and follow this and see if that makes sense to you. Okay, let's do another one. Here is another one. Now in order to do this, we have to know antiderivative of this. Again, we know that antiderivative of cosine x minus 1 dx, you can separate it into antiderivative of cosine x dx minus antiderivative of 1 dx. Now we know derivative of sine is cosine, so antiderivative of cosine is sine. Minus, and we know the antiderivative of a constant is just that constant times x, which is just x, right? So that's the antiderivative for this function right here. The antiderivative of it is this. Okay, now we can do it, right? We can just substitute. Let me show you the work. So it's antiderivative at pi over 2 minus antiderivative at negative pi over 2, right? And there's a notation here. Let me go back and also talk about notation in this example. So the notation is this right here. So when we find the antiderivative, then we can put this brackets, one, maybe this one only, or both, doesn't matter. And we put the function in here, the antiderivative function, and we put the limits here. That means what? That means evaluate this at 1. So that means evaluate it at 1 and then subtract the same function evaluated as 0. That's what this notation means, right? It means put 1 for the variable here first, and then minus is part of the formula, and then put the 0 in there, and then do the operations. Okay, so for this example, the antiderivative again is what? Is sine x minus x. And here's another notation, sine x minus x. Instead of using brackets, sometimes we just use a segment, and then we put negative pi over 2 here and pi over 2 here. That's the same thing. It means put pi over 2 here for x and here for x, and then put negative pi over 2 here for x and here for x, and subtract them. So again, minus comes from the formula. Minus is there. This minus is not this minus, right? This minus means you evaluate whatever you have here at pi over 2, then subtract from it whatever you get if you put this in it. Okay? So sine of pi over 2 is 1, of course. You know, sine of pi over 2 is 1. And sine of negative pi over 2 is negative 1. So sine of pi over 2 is 1 minus pi over 2 minus sine of pi over 2 is negative 1 minus minus pi over 2. So that means basically that would be plus 1, and then this would be minus pi over 2. So we're going to have minus pi over 2 minus pi over 2, that's minus pi. And then 1 plus 1 is 2. So that's the answer. Okay, now here's another one. Again, what's the antiderivative of x squared minus 2x plus 3 dx? Well, we can separate it into antiderivative of x squared dx minus antiderivative of 2x dx plus antiderivative of 3 dx. Antiderivative of this is x to the third over 3. This one would be 2x to the second over 2, and that would be 3x, right? All right, so I'm going to show you that right there. So that's the antiderivative, and then we have to evaluate it at 1, and then subtract, evaluate it at 0, right? So if you put a 1 here and 1 here and 1 here, you get this. If you put 0 here, 0 here, 0 here, you get this. And the answer is 7 over 3. So the area under this function, which you see over here from 0 to 1, is 7 over 3. And you can easily tell that the area is kind of between this rectangle and this bigger one, right? Now the smaller rectangle is 2 units, the area, and the bigger rectangle is 3 units. So the actual area we want, we know is between 2 and 3, but what is it exactly? Oh, you never find out without calculus. Exactly is that. If I wanted, I could, again, do method of exhaustion and get closer and closer to this, but you can never get here without calculus. All right. So in general, the first part, I'm going to add a general formula for first part. In the first part, we said that if we define f of x to be basically f of t dt from a to x, then f prime is going to be what? Is going to be f of x, right? But we can do better than that. what if the limits are themselves are functions? So if that's the case, then the derivative would be, if you put this function for t, and then put this function for t and subtract, but you have to use chain rule. So you're going to go f of q of x times q prime of x minus f of p of x times p prime of x. Now let me give you an example to make this clear. Suppose we have an example like this, right? Now, this is what we want to take derivative of, right? Now, we're going to assume that the antiderivative of this function we don't know. But the antiderivative, whatever it is f of t, capital F of t. That's the antiderivative of e to negative t to the third power. We don't know what it is, but that's okay, we don't have to. Because by the fundamental theorem of calculus part 2, we know that the answer to this, right, not the derivative, but the answer of this definite integral is basically this, if we assume that this is the antiderivative. We don't know what antiderivative function is, but whatever it is, if we put x to the third there, and we put x to the second there, we can subtract and we're done. Now, what's the derivative of this? If I want to take the derivative, it's like you're taking derivative of both sides because they're equal, right? So derivative of this equals to derivative of this. What's the derivative of something minus something? Well, it's derivative of something minus derivative of something. How do we take derivative of a function? Well, we use chain rule. What's the derivative? What's the derivative of capital F of x to the third? By chain rule, that would be f prime of x to the third times what? Times the prime of x to the third, right? That's what that is. So we're going to apply that to this part and apply that to this part, and notice what we get. We get exactly what we have here, right? So now we know whatever capital F of t is, if you prime it, you end up with what? You end up with e to negative t third, t to the third power. So we know f prime of t is what? Is e to negative t to the third. Why? Because we assume capital F is the antiderivative. So if you take derivative of it, you should get that. Okay, now, we know that. I've given you it right here. Now, what we have to do, we have to find f prime evaluated at x to the third power. So we have to take x to the third and substitute for t here. And we're going to get this. And then we have to take e to negative t to the third, which is f prime, and evaluate it at x squared. What is that? Well, that's going to be x squared. You should substitute x squared for t, right? And you're going to get e to negative x to the sixth power, right? So if we take this and evaluate it at x to the third, we did that, or I did that already for you here. Well, that's the answer. But what do you get if you evaluate it at x to the second power? Well, you get e to negative x to the second to the third, which is x to the sixth. And that's how I got negative x to the sixth. All right, so that's the structure, and you see this structure is exactly what that formula is all about. So you don't have to go through all this, right? So if you're given something like that, right, all you have to do, if you know the antiderivative, just substitute substitute and get it. But what if you don't know the antiderivative? And we don't really need to know antiderivative if you just want what? If you just want dx, d over dx. If you want to take derivative of this, you don't have to know this. You can skip that and go directly to what? This formula. Just take x to the third and substitute here. So you get negative x to the third to the third, and then multiply it by derivative of x to the third, which is 3x squared. right? And then minus, now take x squared and substitute there, so it's going to be e to negative x squared to the third, right? Times what? Times derivative of x squared, which is 2x. And you're done. That's it. You don't have to go through all this. The reason I did this is to show you that this actually works, the formula. And what we end up with is exactly what we have here. All right, so that's the general formula to use when you want to do derivative. Here's an example. Well, that's easy. We already know that, right? That's very easy. Here's another one. So what's the derivative? Well, derivative of this, all you have to do is put this in here and put this in here, right? But since this is a constant, we don't have to get it involved, because what happens if you get it involved? Well, you're going to get 0. See that? Because what's the derivative of a constant? Is 0. So you don't really have to subtract anything. You could just, if it's a constant and there's a function here, all you have to do is substitute that over here. So the answer would be 1 over x to the third to the second. You see, I put x to the third for p. And then multiply by derivative of x to the third, which is 3x squared. You don't have to subtract anything. If you do, you get 0. So if this is a constant, you don't have to use the second part here. So the answer is this right there, which simplifies to that. Okay? Now, here's an example where we are not going to be able to use the fundamental theorem of calculus to find a formula for this and then just substitute and find the antiderivative function. We're not going to be able to do that. Why? Because this is a type of function where if you try to find the area function, the formula for it, there is no formula. But what if you have an observation from some application problem and you have this function, which happens actually in the science of optics. You get expressions like this when you work with angle of reflections and all that with lenses, right? You end up with a formula like that, and you want to know what the pattern is, so you need to, to integrate this, and we don't know how to do that. There are no formulas for that. So how do we find the S of x, which is the pattern that we actually like? Because that gives us, these functions give the laws in physics, right? So the laws to work with lenses come from what? Come from this pattern. So how do we do that? Well, we are going to, let me go to do the same thing that we did before, remember? We created that point A, and then we used the point A to find the function values. So that's what we are going to do. I'm waiting for this to download completely. Looks like it did. So you can actually, I could just animate it here. There. You see, as the area function, as the we evaluating the different values for the area under this curve, which is this curve right here, this is the area function. So that's something amazing here. We are graphing something that we have no formula for. No exact formula, algebraic formula for this red function here. But we know what the values are. We can actually apply it in application problems, right? So that's the power of calculus and also computational analysis that we can do to find the patterns that we need. Okay, so that's what that is. And here is another example. And I want to connect this idea of what happens. So we know this is the, we know that if we take f of t dt, and we start with some, fixed point here and make this x, this would be the area function, right? What happens if we change this? What changes? Well, remember, the area function is antiderivative. And remember, antiderivative is a family of functions. So this number changes which member of the family you're going to get. Okay, that's how it is. So for example, let's say we want to find the integral of sine t dt from a, some constant a, to x. Now we know the answer to antiderivative of sine is negative cosine, right? The antiderivative is negative cosine. Now, we discussed this at the end of chapter 4. So, negative cosine, but remember there is plus c here. What determines that c? That number determines that c. Now, let's see what we get. So, if I do this antiderivative, since we know the antiderivative is negative cosine for sine, if I want to do this, according to fundamental theorem of calculus, that would be f of x minus f of x, at a, right? So it would be this, which is this. So this is a family of functions depending on a. So, and they're all negative cosine functions. So let me show you what we get. So you see here, if I change the different b values, let it load for a second. Still loading. All right, there you go. So when I move this, I create the area function, right? And notice my a is at 0 right now. What is cosine 0? Cosine 0 is 1. So that means the antiderivative, the red one, created by the dots, the red dots, that is the antiderivative when a equals to 0. And looks like that's the antiderivative when a equals to 0, c equals to 1. So that means the antiderivative, which is the negative cosine function, has moved up by 1 unit. Okay, that's what it means. Now, what value of a gives me the antiderivative function that is just negative cosine and doesn't have this x, this c is 0? Well, think of what is cosine of what number is 0. Cosine of pi over 2 is 0. And pi over 2, so let me go here, and for initial value, I'm going to put pi divided by 2. There. And now, if I do that, my area function is going to be negative cosine. Look at the, let me move this a little bit so I can get more points so we can see the shape. So notice this red function right here, created by the red dots, is actually negative cosine. You see, it starts from here and goes up and then comes over here. That's negative cosine. Because remember, cosine has to start from here and go this way, right? This is negative cosine, and looks like that the middle is 0. So this number, cosine of pi over 2, is 0. Okay, so that's the connection of the c to the initial value a. That's how they're connected. All right, so I'm gonna stop this video here and make another video to discuss the next section. Okay, so I see you in the next video. Take care of yourself and others. I'll see you next time.